It's Kristen Atchison again, and we're going to be talking about more in depth about factorial designs, primarily about the main effect and the interactions that we can look at using factorial designs. So a main effect in a factorial design is the overall effect of an independent variable in a complex design. So it's just looking at one of the independent variables. The key to think about is it's the effect on the dependent variable as if only that one independent variable was studied. So if we were doing a study that looked at, again, drug dosage and age on symptomology, and we found, we were looking at, again, just one of those independent variables. We just looked at age. A main effect of age would be the effect of symptomology on the effect of age on symptomology as if we didn't even look at dosage, as if we only did this study as a one-factor design. We're pretending, in fact, that it's a one-factor design when we look at main effects. We're pretending that we're only looking at this one factor. And the same is true of the other main effect. So it would be looking at the main effect of dosage then on symptomology, as if we didn't even look at age, as if we're just pretending that we only did that one study. And so by doing a factorial design, we're in sense doing two little experiments, and two experiments within one. We can look at them individually as if we didn't do the other part. We can look at them in a way that only is looking at the main effect of one independent variable, pretending that the other independent variable wasn't even there. Interactions effects are that added thing that we get, that we can do with factorial designs that we can't do in a one-factor design. Main effects is what we look at in one-factor designs. When we're getting an effect, that's a main effect. But an interaction is this combined effects of both of them simultaneously. So looking at them both together. So not only are we not pretending that we didn't do the other independent variable, now I want to see what influence they had on each other. How did those work together to cause changes on the dependent variable? An interaction effect occurs when the effect of an independent variable differs depending on a level of the second independent variable. That means that something different is going on when they work together than when they work alone. So if we look at a main effect and we see that there's a main effect of age, and we can explain it just based on age. And then we look at the results and we see a main effect of dosage, and we can explain that main effect just because of dosage. Interaction tells us that something different is going on outside of these two main effects. Something different is going on. There's an interaction where we have different responses depending on the different levels of the various conditions. And we'll get into some more examples of those so you can kind of see how these things work. So again, back to our example of Barbie M and the neutral picture book across young girls in kindergarten, first grade, and second grade. Remember, again, this is a 3x3 design. We have two independent variables, the version of the picture book and grade, and each one of those has 3 levels. That gives us a factorial combination of 9. And again, what's important to know is that we're pairing each one of these with each other level. So Barbie in kindergarten have a pair, Barbie in first grade, Barbie in second grade, M in kindergarten, M in first grade, M in second grade, neutral. So we have this factorial, and that's how we get to that 9 factorial combinations, is we pair each level of one independent variable with each level of the other independent variable. A main effect is, again, looking at these things as if we just looked at the effect of grade, or we just looked at the effect of picture book. So if we were looking at a main effect of grade, of kindergarten, first grade, and second grade, and we wanted to know if there was a change in body dissatisfaction scores across age, we would look at just the means of kindergarten, first grade, and second grade, pretending that we didn't even look at the version of the picture book. We didn't even study that. These are the results we would have expected if we didn't even look at that, because this is the average of those 3. So this is the average of kindergarten results. 1 plus 2 plus 3, the average is 2. For the average of first grade results, 4, 5, and 6, the average is 5. For the average of second grade results, 7, 8, and 9, the average is 8. for the version, and we would be able to say then, it looks like there is an effect of grade. We have a difference in mean. We don't know this statistically yet, but we can look at it and say that 2 is bigger than 5, which is bigger than, and 8 is bigger than both of those. We can look and see those differences in the numbers. And so we're able to say that we think that there's a main effect of grade. We don't know this statistically, but it appears that there is a main effect of grade, that made a difference in the means. That the older kids get, the more increased body dissatisfaction they have. Now let's pretend that we didn't even look at grade. We only looked at the version of the picture book. We only looked at this manipulated variable of picture book. And so we're going to collapse across grade. We're going to pretend that we never even looked at grade. We're going to pretend that we just did Barbie, M, and neutral. That was the only thing that we looked at. So we take the average of 1, 4, and 7 for Barbie, and we get 4. We take the average of 2, 5, and 8 for M, and we get 5. And we take the average of 3, 6, and 9 for neutral, and we get 6. And we look at those book means and say, are those different? Do we think those are different? Well, it looks like they're different. We don't know if that's statistically significant, but it appears that there's a main effective age because 4, 5, and 6 are different. It appears that we have the highest self-esteem with neutral as opposed to Barbie or M. And so again, that's what they did. They looked at these main effects, and they found a main effect of picture book, that Barbie images caused greater body dissatisfaction than the M and neutral images. They found a main effect of grade, that body dissatisfaction increased as grade in school increased. And when they looked at the interaction, that would be the combination of both of them together, was there something different going on? In the sample data given, not necessarily in their actual findings, there was no combined effect seen. So in the made-up data I gave you on the previous slide, there was no interaction. So here are some more examples. This is hypothetical data showing the means of a two-factor study. Again, it's our alcohol and caffeine study. And this example that they've given us is where we have mean effects, but we have no interactions. How we can tell is, again, we look at the means. So if we're looking at the main effect of alcohol, we want to just look at alcohol. We want to pretend that we didn't even look at caffeine. So we'll take the average of 625, 600, and 575, and we get 600. We take the average for alcohol of 675, 650, and 625, and we get 650. And we look at those means. Are 600 and 650 different? Well, I think they are. They're different. I don't know that they're significantly different, but they appear to be different. So there appears to be a main effect of alcohol. We'll do the same thing for caffeine. We'll look at caffeine as if we never even looked at alcohol. So we're going to collapse across those alcohol scores. We're not going to look at those individual cells, and we're just going to look at the means. So we look at the caffeine then had a mean of 650. No caffeine had a mean of 650. 200 milligrams of caffeine had a mean of 625. And 400 milligrams of caffeine had a mean of 600. Well, those are different. 650, 625, and 600 is different. We don't know that those are statistically significant, but it appears that there's a main effect of caffeine. Now to look at interaction, we need to see if the information of the main effects explains any differences in the individual cells. So primarily here we've been looking outside of these individual cells. We've kind of collapsed across and we've only looked at either alcohol or we've only looked at caffeine. Now we want to actually look at this interaction. So we want to look at each individual cell. We want to see what's going on. And we need to see if the main effects are explaining any differences we see in the cells. So the best way to do that, or the way that I find is most useful, and there's different methods, and your book can discuss some additional, is you look at these means. So say if we're looking at the difference between alcohol and no alcohol, the difference between 600 and 650 is 50. Okay, so we have an effect of 50. Well, let's see if that effect of 50 is what's explaining the differences within our cells. So when we look at 575 and 625, is that still the effect of 50? It is. 600 and 650, is that still our effect of 50? Yes. 625 and 675, is that still our effect of 50? It is. So we don't have anything different happening there that can't be explained by our main effect. We'll do it for caffeine as well. So we have a difference of 650 and 625 between no caffeine and 200 milligrams of caffeine. That's a difference of 25. So let's look within the cells. In the alcohol, no caffeine, we have 675. In the 200 milligrams of caffeine and alcohol, we have 650. That's still a difference of 25. So our main effect is still driving any differences we have in individual cells. Let's look at the no alcohol, 625 and 600, same thing. We still have that 25-point difference. Our main effect is still driving any of these differences. We'll do it for 200 milligrams of caffeine versus 400 milligrams of caffeine. It's again a 25-point difference. And if you look inside the cell, 650 versus 625, the main effect is still explaining that 25-point difference. 600 versus 575, we're still explaining that 25-point difference by our main effect. And we can even look at no caffeine versus caffeine. We've got a 50-point difference there. Again, those individual cells within, the differences in them are again driven by these main effects. There's nothing different going on that's not already been explained by our main effect. And that's what an interaction is. An interaction is there's something different going on that can't be explained by our main effects. We can explain any of these differences in these individual cells, these 6 different conditions we had, by these main effects. We can explain them already by saying that there's a main effect of alcohol and there's a main effect of caffeine. We've already explained those. And so we have no interaction. Here's what that data looks like graphed. And we can again see that there's a difference in response time. We have the longest response time with no caffeine and alcohol. We have lesser response time with no alcohol. You can see that those 2 lines, we always had a faster response time with no alcohol than alcohol. But we also always seem to have a faster response time with more caffeine versus less caffeine. So again, you can see both of those main effects. How we can tell that there's no interaction here without doing those same kinds of differences is these lines are parallel. If these lines are parallel, then we can explain, it's telling us that we can explain everything that's going on by any kinds of main effects that are there, if any, but that there's no interaction going on. Here's that same hypothetical study and that same hypothetical means on the outside for our main effects, but this time they've manipulated the data to show us an interaction. So again, we have a main effect of alcohol that's 50. If we go into the 400 milligram caffeine condition and we look at no alcohol versus alcohol, do we have a difference of 50 there? Is it just explained by the main effect? No, we have a difference of 20 there. 200 milligrams of caffeine is still a difference of 50. And if we look at no caffeine, we have a difference of 610 and 690. That's more than 50. We've got an 80-point difference there in response time in milliseconds. So again, something different is going on than we can be explained by just the main effect. The same thing if we look at caffeine, we still have those 25-point differences. So if we look at the difference of no caffeine versus 200 milligrams of caffeine, for the participants that received alcohol, we should have that 25-point difference if all that's going on is the main effect. But we don't. We have a 40-point difference. So something different is going on than we can explain just by the main effects. So to look at main effects, you're going to want to look at the means on the outside. We're collapsing across this raw data. You don't even look at this raw data in the individual cells to look at main effects. You only look at these outside means. When you're looking at interaction, because we're trying to look at how these things are interacting with each other, that's where we're going to want to look at these individual cells, and we're going to want to look and see if something different is going on there than we saw in these outside conditions. Here's this data graphed. You see that these lines are no longer parallel. They're converging. If we continued them, they would touch. And that's what you see with interactions. You're going to see either crossing lines, you're going to see converging lines such as this, where they're getting closer to each other as we increase the amount of caffeine, or you'll see diverging lines, where they're going apart from each other. Any non-parallel line is a sign of an interaction, that there's something else going on that can be explained by just the main effects. Here's another example. This is a study that's looking at the relationship between the TV viewing habits of 5-year-old children, and then the dependent variable is their future high school grades. And the two independent variables that they looked at was the amount of time that 5-year-old children spent watching TV. And then that was one independent variable, either small to average amounts or large amounts of time. And the other independent variable was the kind of programming they were watching. Were they watching educational programming? Were they watching PBS Kids? Or were they watching SpongeBob SquarePants, non-educational programming? And the difference, and any difference that made. And what they did then is they recorded in high school these high school grade averages. And that was our dependent variable. So again, if we're just looking at the data, we can look at the difference between small amount and large amount. Did the effect of just how much TV make a difference on grades? And what we look at is no, it didn't. Both of them had a mean of 77. It wasn't how much TV that you watched that really influenced high school performance. If we look at educational versus non-educational programming, we look at the difference of a mean of 83 versus 71 for the type of programming. And what we see that there is a difference. We again don't know if that's statistically significant, but it appears that there's a main effect of the type of programming on high school performance. And then we'll take those same numbers and we'll look inside the cells and see if we can explain what's going on inside the cells by just our main effects as a whole. So we have no difference between the amount of TV watched, small versus large, in our means. We have 0 mean difference there. So if we look at the difference between small amounts of TV and large amounts of TV for people watching non-educational programs, we see a 10-point difference in those cells. Now, if we just were dealing with the main effect here, we wouldn't see that difference. Already, by just seeing that one difference, we know that there's an interaction because we know something different is going on inside the cells than is going on outside the cells. We can't explain the differences inside the cells based on our main effects, the differences that we're seeing outside the cells. If you look at the graph now, we have on the x-axis, we have the amount of time that the 5-year-old children were watching, where we have small to average on the left and large amounts on the right. On the y-axis, we have the high school grade average. And then the lines, we are representing that second independent variable of the type of programming, either educational or non-educational. Well, first off, right off the bat, these lines aren't parallel. So we can tell that we have an interaction going on here. We can see that interaction really, really clearly. And again, that's the best way to see an interaction. Doing it mathematically the way we've discussed also works. It's easiest to do it visually. And so sometimes even I will take this data and graph it and see if I see those interactions. Sometimes that can be easier to do. It really just depends on which way you prefer to see those interactions. But it is important to know that you can check for interactions just by looking at a graph without even looking really at paying attention to the means. So let's go through the various examples in pretend data, in a pretend study of independent variable A and independent variable B. This is a 2x2 design. We have 2 independent variables. Each one of those have 2 levels. This is completely made up, but this is what data might look like with no effects. We see no difference between independent variable A. 10 and 10 are the same. And we see no difference between independent variable B. 10 and 10 are the same. If we look at those differences inside the cells, again, we see nothing different is going on there than is going on outside the cells. All of the numbers are 10. If we were to look at the graph, and we could draw lines B1 to B1, B2 to B2, those lines are parallel and even actually overlap in this case because we have no main effects either. So not only are they kind of parallel, they're actually on the same line almost because we have no main effects as well. This is what a main effect of A would look like. We have a difference between level 1 and level 2 of A. 8 and 12 are different, but there's no main effect of B. There's 10 and 10 are the same. And there's no interaction here because that 4-point difference we see between 8 and 12 is carried on within the cells, and there's no difference between 12 and 12 and 8 and 8 that main effect of B. So again, here we only have a main effect of A. We can explain all the data just based on this difference of level 1 versus level 2 of A. If we were to, again, draw lines here from B1 to B1 and B2 to B2, again, we see these lines are parallel, which again indicates that there's no interaction here. A main effect of B. Here we have B1 and B2 are different. We have that 4-point difference there, but we have no difference on A1 and A2. 10 and 10 are the same. And again, the data within the cells is explained by the main effect of B. And again, if we draw lines, B2 to B2, B1 to B1, we have parallel lines. Again, these lines are not crossing. We have no interaction. Here's the main effect of A and B. So we have the 4-point difference for A, and we have a 8-point difference for B. If we look inside the cells, that holds up. 8 and 16 is an 8-point difference. 12 and 4 is an 8-point difference. If we look at our difference between 8 and 12 for the main effect of A, we have a 4-point difference. We look in the cells, 4 and 8 is a 4-point difference. 12 and 16 is a 4-point difference. We have a main effect of A because 8 and 12 are different, and we have a main effect of B because 14 and 16 are different. But the individual cells inside are explained exclusively by these main effects. Nothing different is going on inside the cells than is going on outside the cells. Again, we could graph this and look at B2 and B2 versus B1 and B1. Again, those lines are parallel, so we know that there's no interaction going on here. This is what an interaction alone would look like. If you look at A1 versus A2 means, 10 and 10 are the same. B1 versus B2, 10 and 10 are the same. We have no main effects going on here. But if we look inside the cells, well, there's something very different going on in there. We have an interaction here. And if you were to draw this, B1 to B1, B2 to B2, we have a nice cross. We have a very, very clear interaction in this study. Not even talking about converging and diverging, we have an actual cross. So again, this is evidence of an interaction. Again, we see something different is going on with the individual cells than we see is going on outside of the cells. There's no main effect, but there is differences with the individual cells. This is an interaction and a main effect of A. So again, we have a difference of A1 and A2. 8 and 12 are different. There's no main effect of B. 10 and 10 are the same. If we look inside the cells, however, 10 and 10, we should see no difference between B1 and B2 on level A2. But we see a 4-point difference. And we see a 4-point difference for B1 and B2 for level A1. So we're seeing something different going on inside the cells. We can't explain those differences by just our main effect or lack of main effect. Again, if we were to draw these lines, B1 to B1, B2 to B2, we see a cross, we see an interaction. And again, graphing this is sometimes the easiest way to see it. If we see a convergence, a divergence, or an actual cross, anything really but parallel indicates that there's an interaction. This is an interaction and a main effect of B. Again, level A1 and A2 are the same. B1 and B2 are not. We are seeing, again, that 8-point difference. If we look within inside the cells, that 8-point difference collapses right away. If you look at the difference between B1 and B2 for level A2, the difference of 8 and 12, there we have a difference of 4, which is very different than the difference of 8 that we have with our main effect. So right there, we already know we only need to find one that's different, has gone on. So we don't even have to look any further because we found that one that is different. Again, if you draw those lines, B1 and B1, B2 and B2, these lines are converging. They're going towards each other. So again, we know that there's an interaction. And here is we've got everything. We've got a main effect of A, a main effect of B, and an interaction. Again, we have differences on the means for A1 and A2. We have differences for the means for B1 and B2. But we have differences for what's going on inside the cells as opposed to what's going on outside the cells. Again, we have an 8-point difference outside for B1 versus B2. If you look inside on level A2, that 8-point difference is already collapsed. We only have a 4-point difference between 10 and 4. So again, we found one difference, something different is going on. We can't explain what's going on inside the cells by the outside of the cells, so we have an interaction. Again, by graphing this, we'll see it as well. B1, B1, B2, B2. Again, these lines are converging, so we see this interaction. Feel free to go back and look at these. I will also put up these individual combinations just for you to look at and see the relationships of these. Again, graphs or figures can be used to detect these interactions really, really easily. It's, again, very evident that there's an interaction when those lines are not parallel in any way, shape, or form. That includes, again, intersecting, converging, or diverging. However, we need to do a statistical test to determine whether that interaction is statistically significant. So again, just because we see these things converging or diverging gives us evidence that there may be an interaction, but a statistical test would be necessary. When I'm asking you about giving you data like that and asking you, is there a main effect? Is there an interaction? I just want to know, is it likely there is one because they're different or not? You're not expected to do a statistical test on that. So again, say whether it's likely there is an interaction or it's likely there is a main effect. Again, you need to do a statistical test to determine if there's statistical significance. Here's another example of those lines converging. This is an example we'll go over in class. Again, you can look at this. You don't know anything about this study. We haven't gone over it yet, but you can right away see, oh, wait, we've got an interaction. These lines are converging on each other. Something different is going on than any possible main effects that are happening. Within interaction effects, there can also be problems with floor and ceiling effects. These are sometime an interaction seems to be significant, but this is by mistake. So sometimes it may look like we have this interaction on these graphs, but it really may be an issue with how we're measuring things. This occurs when the means for one or more conditions reach on average near either the highest possible score, which is a ceiling effect. So that means like if your test, you can only get 125 on your test and everybody's getting 125, we have a ceiling effect. Everybody's at the top. Whereas if everybody, this has never happened, and I hope it never does. Let's come up with a different example. If you had, let's say, desire for sweets, and it was how many cookies do you want, and everybody had like 0. Nobody wanted any cookies. Well, it may be your kind of cookie. You may have a floor effect. Nobody wants any of your cookies because there's some strange looking cookie, or maybe they're moldy cookies. We're all by the lowest possible score. There's a floor effect. And when this happens, any interaction that it looks like there may be is actually uninterpretable because we don't know if we were to extend the ceiling or extend the floor, if that would still be there. Here's an example of that. Here's an example where we're looking at test score based on the 2 independent variables they looked at were the number of hours that they studied, whether they studied 10 hours or 15 hours, and the kind of test that they were given. The red line is an easy test and the yellow line is a hard test. Well, here it looks like they're in interaction because these lines are not parallel. But it may just actually be that we just didn't have enough questions on the test. Our easy test was too easy. And so everybody, with 10 hours of study, we're almost by the ceiling. We get to 15 hours of study and everybody maxed out at 50. So we can't interpret if there actually is an interaction effect here because we're at that ceiling. So if we have enough room in our dependent variable, say we increased the number of questions on our test to 70, then we can see that there actually is not an interaction here between the kind of test and the hours studied, the difficulty of the test and the hours studied. We actually see 2 parallel lines because we've increased that ceiling. We can stretch out that and see that there's not an interaction. So again, if we're hitting either the ceiling, the top of our dependent variable measure, or the bottom of our dependent variable measure. We need to kind of look at what's going on, and we cannot interpret any interactions based on that because we're either at the floor or the ceiling, and subsequent studies would need to be done to investigate that. So I hope that helps with main effect and interactions. You do have a participation question that it's available on D2L. Please do that and bring it to class on Wednesday. If you have any questions, feel free to let me know.